Hello everyone, welcome back to Random Matrix Theory. So today we will talk about random matrix models. Okay, first, a random matrix, which we'll often say Rm, is a matrix whose elements are randomly distributed. That is, the elements of a random matrix, that is, the matrix elements, are picked randomly from an ensemble. It can be a Gaussian ensemble or whatever. So we pick the elements from a random distribution. So random matrix, or a random matrix integral, is characterized by a matrix ensemble, let's call it E, and a complex measure d mu of m for m belonging to the ensemble. So these are the two things that we need to characterize a random matrix. And if you remember, an ensemble is basically creating n copies of a system and randomly picking one copy and doing experiments or analyzing the copies of the system. For example, if you can take n copies of your mug and do various experiments on that mug and give a statistical analysis of certain characters of your mug. So that is an ensemble, that is creating n copies of a system and performing certain tasks on the system. You can perform certain tasks by picking things randomly from that system. And a complex measure, we need that to define the partition function or a matrix integral. So first, the partition function is defined as, let's call it curly z, and this is how we define a partition function for corresponding to matrix models. Previously we saw certain specific examples. For example, if you remember, one of the examples where this is a single matrix model, that it involves a single matrix plus, let's say, G of Vm. These are the matrix models that we considered in our previous discussions, and the partition function we defined here is a more generalized case. That is, it can have non-Gaussian part here and different kinds of matrix integrals, basically. So a partition function for a random matrix model is defined, for random matrix models are defined in this way. Okay. Also, I should write what Vm is. Quote. It's like, it can be a sum of p greater than equal to 3 trace of m to the p. We consider cubic and tetravalent vertices or vertices with valency 5 and so on. Next, we need to define another quantity called the expectation value or moments. We define them in this way: the angle brackets of f of m, that is a function of m, and the expectation value of that function should be the curly z, and it's e d mu of m. This is how we defined expectation values, and for those who have done a course on probability, expectation values sometimes are like this in the mathematics literature. It's something like this. This is sort of more of a physics notation which we will use throughout the course, but this is a notation that you might have come across in a standard probability course. If you remember, this expectation value is a more general case of our correlation functions. If you remember, our correlation functions were something like this. I'm writing it without the indices, of course. And yeah, so the expectation value that I defined here is a more general case. So general case. So why do we need it? The idea is we can calculate different kinds of quantities corresponding to different quantity. We can calculate quantities of interest. For example, you can calculate quantities like resolvents, thermal partition function if you are doing physics, or so on. And you can also calculate quantities like any random arbitrary quantities that you can find interesting. You can calculate their expectation values. This is very similar to a one variable case. In probability, the one variable case is something like this: f of x and your probability distribution function, and so on. This is what you do in a standard probability course, and if you remember, it's very similar to that. Okay, now if you remember, at the beginning of the lecture I told you that a random matrix is characterized by an ensemble and a complex measure. So let's first discuss the ensemble types. So if you remember the Wigner surmise, which is an eigenvalue distribution, that is the spacing between eigenvalues that we learned in the last video. That is, if you remember Wigner surmise, it's given by, or let's use S, that's better because the distribution is for the spacing between the eigenvalues. It has the probability distribution, or the distribution function is something like this, where the parameter this should be S squared, where the parameter beta belongs to 1, 2, 4. So when Wigner first came out with this, I told you in the last video, he looked this beta corresponded to different symmetries of a nuclear physics problem that he was dealing with. In our scenario, we'll see that they have a very specific, or they have a very interesting, they correspond to very interesting things. So beta, for now, consider beta can be 1, 2, or 3, 1, 2, or 4, and C of beta and A of beta are constants, or are sort of like normalization constants, and they correspond to, let's write it like this, correspond to make the case such that T of S, P of S, those who have done the midterms, solved this problem in the midterm, those who got a certain set, and yes, so the constants, these two constants are oriented in such a way that our normalization holds. That is, if you normalize the integral, it's 1. So they are oriented in that way, and for different betas, this constant will obviously be different, so that our normalization holds. Okay, so different values of beta, we'll consider now different values of beta, and they correspond to 3 so let's write it up. Different values of beta correspond to 3 matrix ensembles. That is, so matrix ensemble whose eigenvalue spacing is approximated by the Wigner surmise are called the Gaussian ensemble or Wigner ensemble. So let's write it like this. Matrix ensembles, we'll now use ME ensembles approximated by Wigner surmise, that is, by this, those ensembles which are approximated by the Wigner, those matrix ensembles which are approximated by the Wigner surmise are called the Gaussian ensemble or Wigner ensembles. So let's explore the different cases of beta. So the first case is called the Gaussian orthogonal ensemble, or GOE, of real symmetric matrices and it corresponds to beta equals 1. That is, if beta equal to 1 in PS, that is here, if beta is equal to 1, the first case, it corresponds to taking an ensemble that is called the Gaussian orthogonal ensemble, and the ensemble is of real symmetric matrices. That is, you have a large set of real symmetric matrices and you're picking the matrix, the values or the elements of the matrix from that ensemble. That is, the matrix, your matrix that you're considering belongs to the Gaussian orthogonal ensemble, which is an ensemble of real symmetric matrices. The second case, beta equal to 2, is Gaussian unitary ensemble of complex Hermitian matrices. Again, this is an ensemble having, this is a Gaussian ensemble of complex Hermitian matrices. That is, our ensemble consists of complex Hermitian matrices. This is what beta equal to 2 corresponds to. The third scenario is Gaussian symplectic. Okay, let's write b equal to 4. The third scenario is Gaussian symplectic ensemble of quaternionic. If you have heard of these numbers, quaternions, it's a more generalization of complex numbers, but we'll not consider that here. So we will almost always deal with these two scenarios. This is just for your reference, because since we are studying Wigner ensembles, so it's best to know that beta equal to 4 corresponds to Gaussian symplectic ensembles of quaternionic Hermitian matrices. That your matrices are quaternionic Hermitian matrices. That is, quaternions are more generalization of your complex numbers. Okay. Now, if you remember, I told you at the beginning that these three types of matrices, the real symmetrics, complex Hermitian, quaternionic Hermitian matrix, I don't remember talking about this, but all three of these, you can look it up, that they have real eigenvalues. All of them have real eigenvalues. So since we'll soon be discussing how to solve a matrix model, so while solving the matrix model corresponding to any of the above three, we almost always make the matrices diagonal, so that we have to deal with the eigenvalues instead of the matrices. Because if you remember, our integrals are matrix integrals, or let's write it like this. So let's see an example. These are matrix integrals, right? So it's very hard for us to deal with matrices in the sense that it's hard to solve the problem, because matrices are, as you can imagine, it's a bit harder to solve compared to, let's say, eigenvalues. These are basically one-dimensional variables, so they're very easy to manipulate. And if by any chance we can turn, let's say, it into something like this, then let's say over d lambda, then it's a Gaussian, right? Or you might, even if it has different terms, we know how to solve those integrals, right? So it's best, and it's almost always done, that we move to the eigenvalue basis. So how do we diagonalize this? That is, let's say we pick a matrix U and we diagonalize it. This is diag lambda 1 eigenvalues. This is how we diagonalize it, the matrix, and move to the eigenvalue basis. Of course, since you're changing the basis, you'll have a Jacobian term. We'll consider that. For now, just think that we are moving to the eigenvalue basis. We are studying the properties. When we explicitly solve, we will take into account all the Jacobians and all the change of variables and everything. But for now, think of it like this, that we are changing the variables to eigenvalue basis, and for that we are diagonalizing the matrix. After we have diagonalized the matrix, we'll see that let's talk about the matrices that diagonalize these three types of matrices. For example, if beta equal to 1, that is GOE of real symmetric matrices, and they are diagonalized by something called circular orthogonal ensemble, which we write as COE. Everything is short in this matrix model literature. So the COE, and it's an ensemble of real orthogonal matrices. So this ensemble consists of orthogonal matrices which are real. So beta equal to 1 is this U matrices corresponds to real orthogonal matrices if M is a real symmetric matrix. That is, if beta equal to 1, we have a GOE, that is Gaussian orthogonal ensemble of real symmetric matrices, and to diagonalize that, we need to pick an element from the circular orthogonal ensemble, which is an ensemble of real orthogonal matrices. Similarly, beta equal to 2 corresponds to GUE of real, okay, that's right, GUE of real Hermitian matrices, and they are diagonalized by circular unitary ensemble of complex unitary matrices. So since you know what unitary matrices are, so to diagonalize that, our beta equal to 2 scenario, U has to belong to, or U has to be a complex unitary matrix. Similarly, beta equal to 4, it's done by CSE, which is complex symplectic ensemble of complex symplectic matrices. To diagonalize it, U has to belong to this. These are the 3 scenarios, and they're the matrices that diagonalize them. So this is a short discussion on ensembles, and very often we'll use ensembles and we'll almost all of the time diagonalize our matrices and move to the eigenvalue basis. So it's best to know what your matrix type is and what you're doing what matrices you're picking to diagonalize them, so we can study them as a whole. In random matrix literature, we often study these things as an ensemble. So if certain things hold, if a certain characteristic holds for a certain ensemble, we know that it holds for a certain matrix, it holds for all of the matrices in the ensemble. So that's why we study these things as an ensemble, or as a very big set, if you want to think like that. So now let's talk about the second thing we need to second thing that characterizes our matrix integral. Let's talk about the measure of our partition function curly z, aka of matrix models. Also, let's not write aka of matrix models. Okay, so on each of the 3 Gaussian ensembles, which let's characterize the ensembles now like this, beta, we can define a measure corresponding to the product of all real components of the matrix. So this is 3 Gaussian ensembles and corresponding to different betas, and this is obviously, this is the distribution. So for each of them we can define a measure corresponding to the matrix, of course, M, which is the product. For those who know a bit of measure theory, it's the Lebesgue measure. It's sometimes called the Lebesgue measure, which is the product of measures of all real components of the matrix. Those who know a bit of measure theory, you know that you can understand that the product of the matrices should boil down to the product of the individual elements of real components of the matrix, right? So dm would be, or for those who don't know, it's just, we're just taking the measure of the matrix, that is dm is equal to dmii, that is the diagonal part, that is real components, that is our components are real, and I less than j, let's define a new index alpha equals 0 to beta minus 1 and dmij. This is how the measure is formed. And it corresponds to different betas. For different betas we'll have different things, and the interesting thing is the measure is invariant under change of basis, and thus invariant under multiplication by a function. Here we are talking about the different properties of our measure, that is our measure will have this property, that trace of, let's say, w m dm. This is sometimes called the potential function, and you understand what is the potential function. You just look at the previous examples that we did. The potential function is for our case it was a Gaussian part plus a non-Gaussian part, that is we have trace of m cubed in addition to negative of trace of m squared. That is the potential basically. So we recover, another thing is that, let's say 2 Gaussian, we get Gaussian statistics, that is it becomes a Gaussian when w polynomial of degree 2. Obviously you have done that. We'll discuss this more in the next video when we explicitly deal with the matrix model and we talk about the solutions of the matrix model. So for now, this is our potential, this is our potential term, which is a function of the matrices. So before I end the video, I want to talk about one last thing, which is, so remember our Gaussian matrices, Gaussian matrix, let's say ensembles, okay, forget it. Gaussian matrix ensembles, they are characterized or distinguished by a parameter, that is beta, which can be 1, 2 or 4. Now you know what 1, 2 and 4 corresponds to. And an interesting thing to note is that even though this corresponds to a Wigner's ensemble, that is these three values, but our measure that we defined before makes sense for any complex value of beta, not just these three. These three gives us the Gaussian statistics, but other than that, Gaussian ensembles, but other than that, it also makes sense. If you want to try something out, it will also make sense. So important thing to note that it makes sense for any values of beta, but these three gives us our Gaussian / Wigner ensembles. But other than that, it makes sense for complex value of beta. So the matrix models that are characterized by beta are called beta matrix models. That is, they are characterized by beta, and we can allow arbitrary values of beta, but this tree will correspond, this tree is our case that we'll be dealing, and this tree corresponds to Gaussian or Wigner ensembles, and it's mostly valid for models that can be written in terms of eigenvalues, but there are a bit of exceptions. But the beta matrix models are basically models that can have arbitrary values of beta, and in almost all of them, as far as I know, they are matrix models that can be written in terms of their eigenvalue distribution. That is, they can be turned into their eigenvalue basis. So this is the beta matrix model, and that is, they are characterized by beta, and the measure looks something like this. So in this video, we introduced ourselves in a more formal language to random matrix models, and we talked about how they are characterized and how different things work in the matrix model scenario. In the next video, we will start discussing about a very specific matrix model. That is, we first talk about the basics of matrix models and how we can plan to solve it. Then we'll explicitly solve a matrix model and move on to other parts of the course. So yeah, thank you.